Okay, so today's notes are on square roots and radicals. Our content objective is to write expressions involving radicals and rational exponents using the properties of exponents. Sorry, rewrite expressions. And our language objective is to use terminology including index, radicand, radical notation, multiplication, and division properties of square roots. So first thing I want to talk about, radical notation. So a radical is this symbol, the square root symbol, but it can have different root numbers in here based on whatever the index might be. So this number that is in sort of in between this little check mark is called the index. And then what's under the radical is called the radicand. So radicand, index, radical symbol, or radical. One important thing to note, especially for this unit, since we're talking about quadratics, is that the invisible index here, so if there's no number written in that little check mark, is 2. So if you don't see a number written in the index, the invisible index is 2, or a square root. You may have already known this, but just to put it on your radar in case it was not. If there's no index written, the implied index is 2, and the invisible index is 2. So let's jump right into the stuff we want to practice today. First thing is multiplication property of square roots. This property says that for any numbers where a and b are both greater than or equal to 0, the square root of a times b, or ab, is equal to the square root of a times the square root of b. So if you are multiplying under here, you can separate this out into 2 separate radicals and then simplify accordingly. Only if you are only multiplying. I want to note that. Also dividing, we'll talk about that in a second. That's why it's multiplication division properties. But you can only separate like this when you are multiplying and dividing in the radical, not when you're adding or subtracting. Only multiply or dividing. So let's see how this can be helpful in simplifying our square roots today. So our first example, I want us to simplify the square root of 50. That's a 50, 50. Okay, so what we can do here, step 1, we're going to separate into factors, or separate the radicand into factors with at least one perfect square. So since we're simplifying square roots, we are going to separate this into numbers with at least one perfect square. So 50 I know is equal to the square root of 50, is equal to the square root of 25 times 2. So I know that 25 is a perfect square, it goes into 50. So I can separate it out like this. Now I can use the multiplication property of square roots to separate into 2 radicals. So I can separate this into the square root of 25 times the square root of 2. And then I can continue simplifying. So I can actually do the square root of 25. I know the square root of 25 is just 5. So I can rewrite this as 5 times the square root of 2. And that would be my simplified form of the square root of 50. So the square root of 50 is equal to 5 times the square root of 2. So I'm going to have us do a quick check here, and I'm going to also show us an alternative method in just a second, but the quick checks I want us to do include, or I want us to simplify. That's our direction. So number 1, I want us to find the square root, or simplify the square root of 300. And number 2, I want us to simplify the square root of 32. I'll show you an alternative method in both of these. So pause it, try it on your own. I'm going to go right now. So I know a perfect square that goes into 300 is 100. So I'm going to rewrite this as 100 times 300, which becomes the square root of 100 times the square root of 3. Sorry, it's 100 times 300, I meant 100 times 3. So square root of 100 times 3 becomes square root of 100 times the square root of 3, which becomes 10 square root of 3. So if you have trouble identifying what perfect squares go into a number, an alternative strategy, which might come up later or be helpful again later when we simplify numbers with different indexes or indices, I don't know, indexes, is finding the factor tree of a number. So if you were not sure how to do this, if you didn't know 100 was a perfect square, if you forgot, or you didn't know a perfect square that went into 100, say you instead split it into 50 times 6. So you didn't know that it was 100 times 3, so instead you did 50 times 6. You can make your factor tree. This is 25 times 2. This is 2 times 3. This is 5 times 5. So this comes down times 2 times 2 times 3. So you can make a factor tree. Since my invisible index is 2, an alternative method, again, you do not have to do this. I think this method is a lot easier, recognizing perfect squares. But if this is hard for you, an alternative method, you can make a factor tree. Since the index is 2, circle pairs, and then you take those out. So you'd have 5 times 2. And then the 3, since it doesn't have a pair, stays under the square root. 5 times 2 is equal to 10 square root of 3. So an alternative way to get to that answer is a factor tree and then pull out pairs if you have trouble identifying perfect square roots or perfect squares that as factors. So let's try the easy way with 32 and then again the factor tree way with 32 in case that is easier for you. So you might recognize that 16 times 2 will give you 32. So 16 times 2 is 32, it becomes the square root of 16 times the square root of 2, 4 square root of 2. That's our answer. Alternative method, you'd make a factor tree for 32. So say you said that is 8 times 4. And then you know this becomes 4 times 2. This becomes 2 times 2. 2 times 2 times 2 times 2 times 2. So I can take out pairs. So I can take out 2 full pairs. So that leads me to have 2 times 2 times the square root of that remaining 2, which is 4 square root of 2. So if that makes more sense to you, you are more than welcome to do it that way. All right, there's one other thing I want to talk about. So I'm going to flip the page for that. It's called the division property of square roots, and I mentioned it a little while ago. It's very similar to our multiplication property of square roots. So the division property of square roots. And what this says is that for any numbers where a is greater than or equal to 0 and b is greater than or equal to 0, I think it's, then you know a over the square root of a over b is equal to the square root of a over the square root of b. This should not be equals to. So just b is greater than 0. So if you have a, square root of a over b is equal to square root of a over square root of b. So similar thing, if you take, you can break this into multiple radicals if you're multiplying or dividing as in the radicand, and only if you're multiplying and dividing in the radicand, not if you're adding and subtracting. Only multiplication and division. So it's going to be a similar process, but some added or different things. So our first example asks us to simplify the square root of 5 over 11. So this time we're going to start with the same step, separate into 2 radicals. So I'm going to change the square root of 5 over 11 into the square root of 5 over the square root of 11. So one thing that's tricky is convention says that, or mathematical convention says that you shouldn't have a square root in the denominator or a radical in the denominator. So I'm going to make a little note of that. Convention says no radicals in the denominator. So this would still count as a radical in the denominator since it's implied that it would end that way. So we're going to multiply the denominator by itself. So step 2, we're going to multiply by the denominator over itself. So what this means is I have the square root of 5 over the square root of 11. My denominator is the square root of 11, so I'm going to multiply that over itself. So because I multiply it by a square root of 11 over a square root of 11, this is just equal to 1 because anything over itself is equal to 1. So when I multiply this out, I get the square root of 5 times 11 because I can use my multiplication property of square roots. And then here I get 11 times 11 or 11 squared. And then I just simplify. So step 3 is going to be to simplify. So then the square root of 11 squared, the square root and the square just cancel each other, and I get the square root of 55 over 11, and that is my final answer. So that gets the denominator clear, and I'm all set. So we're going to just do a couple quick checks to make sure that's clear, and then we'll be done. So I want us to simplify. For the first one, the square root of 6 over 5, and the second one, the square root of 7 over 2. So try those out. I'm going to go over them now. This becomes the square root of 6 over the square root of 5. I need to get that square root out of the denominator. So I multiply it by the radical or the denominator over itself. This becomes the square root of 30 over the square root of 5 squared, or 5 times 5 is 5 squared. The square root and the square cancel each other, and I'm left with the square root of 30 over 5. And that is my final answer. Same process yet again. I have the square root of 7 over the square root of 2. Multiply it by square root of 2 over square root of 2. Becomes the square root of 14 over square root of 2 squared. Square root and the square cancel, and I have the square root of 14 over 2. And I am all set. All right, make sure you write down any questions, comments, or concerns you have on this stuff so we can go over it together in class.